Welcome to lecture 12. Today we are going to discuss about maximal ideals. So, let us start. So, in the last lecture I have finished with one question, and the question was what kind of property an ideal I should have, so that if you are in a ring R and I is an ideal, then what kind of property, what property of an ideal I will imply that this quotient will become a field. That is what we will try to answer in today's lecture, and that is where we introduce the notion of maximal ideals. So, let us first get the motivation. What does it mean by saying that R quotient I will be a field? So, if I want to say that R quotient I is a field, then I know that a field has exactly two ideals, the 0 ideal and the unit ideal. So, from there we will try to understand what kind of property this ideal I should have. So, if R quotient I is a field, then R quotient I has exactly two ideals. R quotient I has exactly two ideals. What are the ideals? The ideal are nothing but the 0 ideal and the unit ideal. So, what is the 0 ideal in R quotient I? That is nothing but the ideal I, because I is the 0 ideal here in the quotient, and this will correspond to the coset 1 plus I. So, these will be exactly the two ideals in R quotient I, but that means that in R quotient I there will not be any more ideals. So, that means any ideal of R quotient I is of the form, we already know, is of the form J quotient I, such that J is an ideal of R, which J is an ideal of R such that I is sitting inside J. So, this is how the ideals of R quotient I look like. So, that means that I do not have any, since R quotient I has only two ideals I and 1 plus I, that means there does not exist any ideal in between these two ideals between I and the unit ideal. So, that is, if we have any ideal, say I contained lying between this unit ideal and this ideal I. So, M is suppose any ideal which is in between this I and the unit ideal, then it will say that R quotient I will have the ideal M quotient I, which is neither the 0 ideal nor the unit ideal in R quotient I. So, let me denote this by 0 bar and 1 bar in order to understand that this bar denote the image in R quotient I, as we are talking in R quotient I. So, that says that if we are having some ideal M which is in between I and the unit ideal, then that will contribute to an ideal in R quotient I, which is apart from the 0 ideal and unit ideal. But I want R quotient I to be a field, that means there should not exist any ideal which will strictly contain I and which will not be the unit ideal. So, this gives you the motivation to define the maximal ideal, and how this definition of maximal ideal comes. So, this definition of maximal ideal is that an ideal I, which is not the whole ring, is called maximal ideal, if there is any ideal that whenever whenever I have some ideal M which is in between this unit ideal and the ideal I, then either this M has to be equal to I or M has to be equal to the whole ring R. So, that means it is not possible that M will be lying in between this proper ideal I and the whole ring. If this is the case, then it has to be equal to one of them. So, that is equivalently saying that I is not contained in any ideal other than I and R. So, I is the only ideal which is contained in I and R. So, there does not exist any ideal which is bigger than I, that means which will contain I and which will not equal to the whole ring. It is not possible. That means, it is in some sense maximal under inclusion. It is some under inclusion, this is the maximal proper ideal which is present in R. So, that is how we define the notion of maximal ideal. But the interesting thing is to say that if you have a non-zero ring, then there will always exist maximal ideal in a ring, non-zero ring. So, we will prove that existence. But before proving that existence, we need a lemma that is known as we need one technique that is known as Jones lemma. So, let me first state the statement of Jones lemma, and then using that Jones lemma, we will prove that in any non-zero ring, remember non-zero ring, there always exists maximal ideal. So, let us try to prove that. So, first I will state what is Jones lemma. You might already be familiar with the notion or with the statement of Jones lemma, but here let me recall it for you quickly. So, let S be a partially ordered set. So, I have a partially ordered set S, and if in that partially ordered set every totally ordered subset, if every totally ordered subset of S has an upper bound, then it says that S contains a maximal element. S contains a maximal element. That means what it says? So, it says that you start with S is a partially ordered set, and in that set if you consider any totally ordered subset and if it has an upper bound, then this set S has a maximal element. So, this I will be using to prove the fact that every non-zero ring there exists in every non-zero ring there exists a maximal ideal. So, let me prove that statement, the proposition that maximal ideal always exist in a non-zero ring. So, let us go into the proof. So, I will be proving using this Jones lemma. That means, first of all I have to define I have to consider a totally ordered partially ordered subset, and then I have to choose a totally ordered subset in that, and then I have to proceed. So, how do I consider? So, I will consider the inclusion operation as the order. So, consider the set S to be nothing but the ideals, collection of all ideals such that I is a proper ideal of R. By that I wanted to mean that I is not the unit ideal of R. Okay. So, if I am considering S to be this set, then this has a partial order with respect to this inclusion operation, and let T be a totally ordered subset in this set S. So, let T be a totally ordered subset of S. That means what? That means that for all ideals I and j in this totally ordered subset T, I should have either I is contained in j or j is contained in I for any two ideals I and j, then either I is contained in j or j is contained in I. So, this is what I wanted to mean when I say that T is a totally ordered subset of S. Then if you consider this U, which is nothing but the union of all those ideals I such that I belongs to T. So, I am considering the union of ideals. So, in general the union of two ideals need not be an ideal, but here I have containment between any two ideals in T. So, in T is a totally ordered subset. So, if I consider the elements of T, then we have a chain of ideals in T in the way in terms of inclusion. So, in this case U is in fact an ideal. So, then U is an ideal of R as T is a totally ordered subset. So, this is something that you should verify, and moreover this ideal U is also not the whole ring, and U is also not the whole ring, that means U is a proper ideal also. So, here I am also saying that U is the not the whole ring, because every element of T these are proper ideals, that not the whole ring. So, their union cannot be, because if the union is the whole ring, that means this identity should belongs to any of one of these ideal, but none of them contains the identity. So, therefore, U is not the whole ring. So, it is a proper ideal, and in fact, we can see that this U is an upper bound for T, and U is an upper bound of T. So, I have started with a partially ordered set S, there I have considered this T to be a totally ordered subset, and I have shown that U is an upper bound of this totally ordered subset T. Then I can say by Jones lemma that S there exists a maximal element in S. So, then by Jones lemma, there exists a maximal element in S, and that is nothing but the maximal ideal, because this is a proper ideal and this is S is nothing but the collection of proper ideals. So, this maximal element is nothing but gives you the maximal ideal of this set S. So, by this we are able to prove that maximal ideal always exists in a non-zero ring. I have assumed it is non-zero because then it is in that ring the multiplicative identity is not the same as the additive identity. So, once this is done, then as a so we observe that the maximal ideal always exists in a non-zero ring, then we will characterize when a quotient can be maximal ideal, that I have already told. So, let me put it as a proposition. So, an ideal M of R is maximal if and only if this quotient R quotient M is a field. That is how we have defined the notion of maximal. We said that R quotient M will be a field if I define M to be a maximal ideal. So, this proof is we have already discussed this thing. So, in order to check whether a ideal is maximal or not, you have to just check whether this quotient ring is becoming a field or not. So, in order to one of this implication is always easy to see, the other implication that I will be proving. So, I will start that M be an maximal ideal, then I will prove that R quotient M will be a field. So, let M be a maximal ideal, and I want to show that R quotient M is a field. So, that means I want to show that R quotient M is a field. That means, I would like to show every non-zero element in R quotient M has a multiplicative inverse. So, since M is a maximal ideal, that will imply that in R quotient M we will have only two ideals. So, since M is maximal ideal, R quotient M has exactly two ideals. Okay. And we have also seen that if you have a non-zero ring which is having exactly two ideals, then it is in fact a field, that we have already shown. So, and this is also a non-zero ring because M is a proper ideal since it is a maximal ideal. So, R quotient M has exactly two ideals and R quotient M is not the zero ring, as M is not the whole ring. Therefore, R quotient M is a field, because we have already shown that a ring which have non-zero ring which has exactly two ideal is in fact a field. Therefore, R quotient M is a field. And if you start with that R quotient M is a field, then we have already seen that is how the definition of maximal ideal is coming. Therefore, M will be a maximal ideal in that case. So, now let us see as an application of this proposition, we get the following corollary, which says that the zero ideal is maximal, is a maximal ideal if and only if R is a field, because I can view R as R quotient 0. So, R is a field is equivalent saying as 0 is a maximal ideal. So, in a field 0 is always the maximal ideal, and if 0 is the maximal ideal in a ring, then it has to be a field. So, this corollary follows from the previous proposition. Now, let me put it as a remark the following fact. So, it says that note that every maximal ideal is prime ideal, because if M is maximal ideal, in R, then I know that R quotient M is a field. If R quotient M is a field, then which implies that it is an integral domain. R quotient M is an integral domain, which implies that M is a prime ideal. Therefore, we have observed that every maximal ideal is a prime ideal. Now, we can ask the converse whether every prime ideal is maximal or not. So, the converse is not true, that is what we will show, but the converse is not true. So, we will give example to show that the converse is not true. So, let us consider the following example. So, in Z you can see that 0 is a prime ideal, but 0 is not maximal ideal, but not maximal ideal, because this ideal 0 is already, I can say this ideal 0 is contained inside any ideal p z where p is prime, all these are proper ideals, right. So, in terms of containment 0 is not the maximal, because I have some, if you consider any number non-zero number, that ideal will always contain 0. Therefore, 0 is a prime ideal which is not a maximal ideal. Moreover, you can look into the polynomial ring in two variables, say c x y. In this case, we can see that this is a prime ideal. Why? Because if I consider the quotient by this, then this is nothing but isomorphic with c y, because here the ideal, the 0 ideal is x, that means all the polynomials which are involves the term x which become 0, that means only the polynomials with variable coefficients in c and indeterminate y will survive. So, this is isomorphic with c y, which is an integral domain, because it is a polynomial ring over a field which is an integral domain, and hence this is a prime ideal, but this is not maximal, but this is not maximal ideal. Why? Because I can consider this ideal x is sitting inside the ideal generated by x and y, which is strictly sitting inside x y. So, in this case you can observe that the ideal generated by x y is in fact a maximal ideal. So, here this c x y quotient, the ideal generated by x comma y is nothing but isomorphic with c, which is a field, therefore, this ideal is maximal. So, here also we have seen one example where the ideal generated by x is prime, but it is not maximal ideal. That means, not always it is true that the prime ideals will be maximal ideals, but there are some rings where we can see that the prime ideals are in fact becoming maximal ideals. So, let us go. So, the remark that I would like to put, that in Z we can see that every non-zero ideal in Z, every non-zero prime ideal, I should say that every non-zero prime ideal is maximal. Every non-zero prime ideal is maximal. Because I know that prime ideals will be of the form p z. So, prime ideals are of the form p z, and z quotient p z is a field. So, p z is maximal. So, we have proved that in Z every non-zero prime ideal is in fact a maximal ideal. This is not only true in Z, but we will observe that this is in fact true if you are considering the polynomial ring over a field. So, in K x polynomial ring over a field, every prime ideal, every non-zero prime ideal is also maximal ideal, is a maximal ideal. So, if I would like to prove that fact, so I know that every prime ideal is generated by an irreducible polynomial. So, I will show that the ideal generated by irreducible polynomial is in fact producing a maximal ideal in K x. So, we already know that let us see the proof. So, we already know that in K x every prime ideal is generated by an irreducible polynomial. So, let I be the ideal which is generated by f x, where f x is irreducible. Then we want to show that this ideal generated by f x, this I is in fact a maximal ideal. So, let me go to the next page. So, basically now we want to show that I is a maximal ideal. So, if I want to show that I is a maximal ideal, then I have to show that R quotient I is in fact a field. So, that is equivalently showing that K x quotient I is a field. That means, I would like to show that every non-zero element in this quotient ring has a multiplicative inverse. So, let us start with an element. So, let G x is an element which does not belongs to I. So, that means, it is does not belongs to the ideal generated by f x. So, that means, G x is non-zero. So, G x bar, the image in R quotient I am denoting it by G bar. So, this is a non-zero element. I would like to prove that it has an multiplicative inverse. Now, since f x is irreducible, that is given. So, since f x is irreducible, therefore, this GCD of f x and G x is nothing but 1. So, from here I can write down 1 as combination of f x and G x. So, I can write it as G x into Q x for some P x and Q x in the polynomial ring, where P x and Q x are polynomials over coefficient in x. Now, let us view this equation in the quotient ring K x quotient I. So, if I view this equation, then this gives me 1 bar is nothing but. So, this is f belongs to f x belongs to the ideal generated by I, that means f bar will become 0. So, this element will not contribute anything here, and I will be left with G bar x into Q bar x. And you can see that G bar x is non-zero because G x does not belongs to the ideal generated by f x. So, this says that Q bar x is the multiplicative inverse of G bar x. Therefore, this implies that G bar x has an multiplicative inverse. So, this implies that every non-zero element has a multiplicative inverse in the quotient ring. Therefore, this quotient ring K x quotient I is a field, and hence it is a maximal ideal. Hence, the ideal generated by f x is a maximal ideal. So, here also I have proved that in the polynomial ring every non-zero prime ideal is in fact a maximal ideal. So, you can see that ring of integers and the polynomial ring over a field behaves almost in a similar way. They share most of the properties which are common in both of them. So, with this I will finish today's lecture, and in the next class I will see the connection between the maximal ideals and the points in a polynomial ring over a field, in fact polynomial ring over algebraically closed field. So, let us stop today.